In algebra, a good deal of time was spent talking about slope. Slope refers to the steepness of a line as it goes through a coordinate plane, and we assign a number to the slope. Slope number. Well, we calculated it like this. Now, by that steepness, I'm talking about this. If this is the line, then is the line going through at this steepness or that steepness or this steepness or like this? Now, if we have a slope that's like this, it doesn't matter whether the line goes through over here or over here. Those lines all have the same slope because they're going through the coordinate plane at the same angle. So we're really calculating that steepness regardless of where in the coordinate plane the graph goes through, where kind of left and right. Okay, so to calculate slope, it's really the ratio of rise over run. If we pick a couple of points like this point and, let's say this point, then when we go from that point to this point, we have a rise of 1 and a run of 3. So we're calculating it loosely defined as rise over run. That's the way you learned it originally. And from this point to this point, we had a rise of 1 and a run of 3. So it's a rise of 1 and a run of 3 for a slope of 1/3. Slope is abbreviated or symbolized with an M, so the slope of this line is 1/3. It's important to know that it doesn't make any difference what 2 points are chosen to make this calculation. I could have chosen this point and a point out here. And between this point and this point, we'd have a rise of 2 and a run of 6. 2 over 6 is still 1/3. We could choose to think about it as from this point to that point. Well, from this point to this point, in terms of rise, you see, we would have to go down 2 and then to the left 6. So it would be a rise of -2 and a run of -6, still 1/3. So no matter how you cook it up, it's still grits. Well, from algebra, you learned that if a line has a steepness like this, if it's really steep from left to right, so think about it left to right, so it's really going uphill left to right. It has a big slope number associated with it. And if you think about it in terms of rise over run, from a point here to a point up here, it might have a rise of 10 and a run of 1. And then you tilt it over a little bit and you have a rise of 5 and a run of 1. You see, and then you might tilt it over a little bit more and you might have a rise of 3 and a run of 3. That's a slope of 1. So the idea is that we have big slope numbers when we're real steep like this, from going from lower left to upper right, and then smaller slope numbers, smaller, 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 then a slope of 1, and then we get into the fractions like this when we twist over, and then it comes all the way down. We're still positive, but we're dealing with fractions now. A fraction like rise of 1, run of 10, 1/10, you see. And then when we're flat like this, when we're exactly horizontal, it's a slope of 0. And you would expect that because big, big positive number, smaller, 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 1, and then fractions, and then 0, you see. And then when we continue to twist around, we have negative values for the slope, and it's negative fractions in here, and then -1 at some point, and then negative big numbers, or big negative numbers for a slope, something like this. And you can test it also. All of these can be tested or thought about in terms of rise over run from one point to another. From like this, for example, if we're talking about a point way up here and down here. From a lower point to an upper point, we might have a rise of 10 and a run of -1. 10 over -1, oh, that's -10. You see, so we can kind of evaluate it like that. But it's important to have a feeling for the slope number as we look at the graph of a linear equation or a straight line. Now, the only slope I didn't talk about is the slope of a line that's vertical. You know, if the line is vertical, if we're just going up and down like this, then from one point to another, from this point to that point, we might have a rise of 10. But what's the run? Well, the run is 0, and the run is the item in the denominator, and that denominator number is 0, which means that the slope associated with this line is undefined. So an undefined slope for vertical lines. Now, this notion of rise over run, it's a very informal way of thinking about it. We had a more formal way of dealing with it, an algebraic form that corresponds with rising and running. You know, we think about x and y values on coordinate planes, x as being horizontal distances and y's being vertical distances. Well, when we're talking about a rise from one point to another, we're talking about a vertical kind of distance. And so the slope then turns out to be, for the rise, we say that it's y2 minus y1. These are subscript numbers. The run, a horizontal idea about x's, horizontal distances, x subscript 2 minus x subscript 1. Subscript numbers are in here only to call attention to the fact that this x-y pair are related to one another. This x-y pair, they're related to one another because of those subscripted 1s and the subscripted 2s. This gives us then a formula for calculating the slope. So we can calculate the slope between 2 points, or the slope of the line that contains a couple of points, given the coordinates of those points, by using the slope formula. Incidentally, we can abbreviate this, and often in calculus we do it like this, as delta y over delta x. The delta meaning change, difference. You see, and a lot of times in calculus we're going to talk about deltas as being very tiny changes, but for this circumstance it's not such a tiny change all the time, but change in y over change in x. That's the whole idea here. Now if we want to find the slope, for example, of the line containing these 2 points, we can do it in a couple of ways. We could use a graphical approach. We could find those points, plot the points on a coordinate plane, and count rise over run if we want to. Let's very quickly put it on the coordinate plane and see where these points lie and maybe make an estimate of the slope. The point 5, 2, let's see, 1, 2, 3, 4, 5 up 2, and the point 1, negative 6. So here are the 2 points. Now what we're probably anticipating here, and the line containing now those 2 points, is we're looking for the slope of that line. And we know it's a positive slope because it's rising from left to right. We know it's a little bit bigger than 1, maybe it's 2, something like that, as the slope number, just as an estimate from our experience. Well, let's see what it actually is. The calculation works like this, and anytime you're using a formula, now we're using a formula for the slope, anytime you're using a formula, write the formula down in the first step. And in the second step, replace the letters with numbers. That is, replace within the formula. No matter how hot you think you are as a mathematician, always, always, always follow that kind of routine. Write the formula down, replace within it. Discipline yourself to do that. It's an organization thing, and we're going to talk a lot about organization as we go along. All right, so we would write m equals, now do we want to use the deltas or do we want to use the y's? I'm going to use the y's and the x's simply to emphasize a point here. I want to make sure that even if we're using deltas later on, we need to make sure that we have a relationship between these 2 items and those 2 items. So we would have then, let's see, a difference in y's. If we use this y first, we would have 2 minus that y. So it's minus negative 6. Don't forget the double minus sign here in the separation with parentheses. Difference in x's, if we used this y first in the numerator, we need to use this x first in the denominator. So we have 5 minus 1. And then when the smoke clears on this, we have 2 plus 6, or 8, and then in the denominator 5 minus 1, 4. 8 over 4 is 2. The slope is 2 as we expected earlier. Now take a look at this linear equation. Here's y equals 2x minus 3. Using the point plotting method, we would create maybe some points to plot here in a table of values. We would plot those points, draw the line. Okay, let's say that we've done that here. Now look at the line in terms of slope. All right, in terms of slope, we can identify the slope number very easily by taking a couple of points and just doing a little rise over run check. Or we could use the slope formula if we looked at the coordinates of the points. But no matter. It's from here to here, we're talking about a rise of 2 and a run of 1. So we have a slope then of 2. Now check out the y-intercept. We talked about intercepts in the previous section. The y-intercept is down here at negative 3. So we have a y-intercept at negative 3. Now look at this. We have a slope here of 2, and the coefficient of x is also a 2. We have a y-intercept of negative 3. We have a constant here of negative 3. Wow, what a coincidence. Well, it's not exactly a coincidence. It turns out that anytime linear equations are in this form, that the coefficient of x will give the slope of the line and the constant will give the y-intercept. And that's why this form of the linear equation is cleverly called the slope-intercept form. So the slope-intercept form of a linear equation. It's a real handy form because it gives so much information. In fact, it is a form from which we can graph. That is, if we didn't know any of this, we could easily graph this rascal by, well, I'll just sketch it real quickly here without all of the commotion of that. I can very easily just take a coordinate plane and identify the position of the y-intercept at -3, and then because I know I have a slope of 2, that's a rise of 2 and a run of 1, and then from that point I can rise 2 and run 1, and then from that point rise 2, 1, run 1, and so on, and I can create as many points as I want to, and I can even create points in the other direction, rise -2, run -1. You see, like that, and so it gives me a way of very quickly sketching the graph. So slope-intercept form. We'll get back to that form in just a little bit. Let's talk about some other stuff. Here, this problem says find an equation of the line with slope of -3/5 that passes through the point -2, 4. Now, you may notice, and hopefully you've noticed before in algebra that much of the discussion, much of the material and technique that is discussed has to do with taking equations and talking about a graphical form, or taking information about a graphical form and then creating equations. So we go graphs, equations, equations, graphs, back and forth, back and forth, back and forth, and the understanding of one simply enhances the understanding of the other. So we're kind of going in that form here. We're talking about information about a graph, and we're asked to create the equation. Well, certainly we could very easily construct this graph, could we not? After all, the graph goes through that point, so we could identify that point. We know we have a slope of -3/5, so we could think of this as a rise of -3 and a run of 5, or a rise of 3 and a run of -5, and from this point we could generate as many other points as we want to and construct the graph without trouble. We could do that, couldn't we? Yes, go like this. Okay, now that we can do that, let's talk about finding the equation. Now, we can find the equation if we just have some kind of formula, some kind of format to put the equation into. Well, it turns out that we can use a variation of the slope formula. In fact, we could use the slope formula itself if we wanted to. But remember, it's just this. Oops. You see, and what we have here, we have the slope, so we could fill in for m, and we have the coordinates of a point, and we could pop those coordinates into this xy pair or into this xy pair. And then we could manipulate this algebraically any way we'd like. Well, if you did this 50 times, you would find out that there's an easier way to proceed. And the easier way is to manipulate the slope formula to begin with and use a form of the slope formula called the point slope form. How clever. We have the coordinates of a point and we have the slope. It's called the point slope form. Very nice. Okay, so the manipulation would work like this. Cross multiply in this form, and we go this way. If we're going this way, we would have y sub 2 minus y sub 1, and going this way we'd have m times the difference in x's. So m times the difference in x's. And usually when we're using this form, we don't use the subscripted 2's, we use the subscripted 1's in there, and we write it like this. So this is the point slope form, or the point slope equation if you'd like. And the reason that the subscripted 2's are left out is to call attention to the subscripted 1's, because the x and y, that's the xy pair we want to pop into. We can do it either way, but if we did it 50 times, we would find out that it's easier to plug into the y1 than the x1. All right, here's how it looks. Now remember, we're going through the point -2, 4. We have a slope of -3/5. So we start out with a point slope form. We replace m with -3/5, the slope. And we are going to pop that value, the coordinates of that point. -2 was the x component, so I replace the x1 with -2. The y is replaced with 4. And then we simply, it's just a matter of manipulation. And let's see, minus -2 is +2. Notice, incidentally, that in the first step up here, I wrote the sort of formula. I wrote the point slope form, or the point slope equation, the thing that we're going to plug into. In the second step, I plug into it, and I don't do anything else. Do not try to begin performing manipulations as you are filling in to some kind of formula. All right, so we just fill in, and now we begin to manipulate. Minus -2 is +2, and -3/5 times the x plus 2. I've gone ahead and multiplied it out here. At this point in the problem, incidentally, we have this is a moment where we can flow with this equation into a general form of a linear equation, which is sort of an ax plus by equals c kind of form, or we can flow into the slope-intercept form. Now the slope-intercept form, y equals mx plus b, now that form, the slope-intercept form, isolates the y on one side. So we would not want to create a coefficient of y. We would want to leave the y over here as it is. And looks like that's what I'm doing here. So I'm multiplying over on the right, expanding a little bit. I'll add 4 on both sides, giving us this. And now I need to collect these two terms. We need a common denominator, which is 5. I multiply the 4 by 5 over 5, getting 20 over 5. Collecting here, I get 14/5. So now I have this in the slope-intercept form. Now, the reason I mention the two forms is because you might manipulate the problem like this and get this kind of answer, and then in the back of the book, the equation looks entirely different. It looks like something not like this. It's more in the general form of ax plus by equals c. And you might think that they're different. No, they're not different. It's just a variation on the same kind of equation. We could have taken that tactic back up here. And I want to show this because algebraic manipulation is a big part of calculus, it turns out. If we're good at algebraic manipulation and we have good organizational skills, calculus is a piece of cake. It's really just a lot of fun. And I hope that's going to be your experience. But at this point, we could elect to eliminate the fraction, you see, and just right quick multiply through by 5. If I multiply through by 5, I'm multiplying that term by 5, this term by 5, and this term by 5. Now notice I'm saying this term. This is one term. It's an indicated product here, so it's one term. So this times 5 would give 5y. This times 5 would give minus 20. And then this term times 5, this term has a couple of factors. I'm electing to multiply that factor, or excuse me, the 5 times this factor, giving -3. You see, we would get that cancellation of the 5s. So we'd have this. And now I would have the 5y minus 20 equals -3x minus 6. And I would probably put the x and y terms on the same side. Remember I said ax plus by equals c form, so I'd add 3x on both sides, giving us 3x over here, then plus 5y equals, and then add 20 on both sides to get -6 plus 20, or 14. So we would have this. And this is equivalent to the slope-intercept form that we wrote earlier. We were talking earlier about the slope-intercept form of a linear equation, and that form is this: y equals mx plus b, where m is the slope and b is the y-intercept. Now, slope, we have been saying, is a ratio. It's a ratio of rise over run. But in working models, in linear models that emulate certain word problems, that slope number is often a rate of change. And using the slope as a rate of change is illustrated in this problem. A mountain climber can climb at a rate of 200 feet per hour if she starts at an elevation of 6,000 feet, write an equation relating time and climbing distance. Now, the problem is very easy to understand if we think about it graphically. And let's think about it graphically first. Let's come over here and create a little sketch of a graph of the situation. We've got a couple of axes here, and let's say the vertical axis is height. And on the horizontal axis, time. So we're starting, the climber is starting at 6,000 feet. Let's say 6,000 is right about here. And after 1 hour, the climber has climbed from this 6,000 level up 200 feet. And then in another hour, another 200 feet. And in another hour, another 200 feet. Now, from the graph, we can see a progression here, sort of a linear progression, and from the graph, we can create the equation that we're after. But this is just a visual idea of what we can do mathematically without the graph, actually. But with the graph, we're talking about a slope here from point to point, a rise of 200 and a run of 1 hour. You see, 200 feet to 1 hour. So the slope number is 200. And the y-intercept is 6,000. So with that information, the height is, and I'm going to write the intercept first because we're kind of starting at 6,000 feet elevation, and then we're adding 200 feet for every hour of time. So its height is 6,000 plus 200 times time in hours. So here's the equation relating height and time. Another idea relating to slope that was studied in algebra is parallel and perpendicular lines. It should seem reasonable that when lines are parallel, their slope numbers are the same. Certainly that's true. It's a pretty intuitive idea. I've got a couple of parallel lines drawn here. I have a couple of them in my hand as well. And obviously, no matter where these lines go through the coordinate plane, when they're parallel, they would have the same slope number. So if these are the two lines, and here's the slope of line 1, there's the slope of line 2, then those slope numbers are the same. It's a little more difficult, though, to understand what happens when lines are perpendicular. If lines are perpendicular, it turns out there is a nice relationship between their slope numbers. But consider that this line would have a slope number that would be relatively large positively. Let's say it's 10. And this one, the one perpendicular to it, would have a slope number that's negative because it's falling from left to right. And also it would be a relatively small number. It would be a fraction. And it turns out that these are just reciprocals of each other. That is, the slope numbers are reciprocals, and in fact negative reciprocals. If this is 10, that's negative 1/10. You see, this slope is negative 1/10. If this is 7, then that's negative 1/7. If this is 5, then that's negative 1/5. If this is 1/2, then that's negative 2/1, or negative 2. So it works like this. If these are the two lines and these are their slopes, then M1 is the negative 1/M2, negative reciprocals. Now, the situation manifests itself in a problem like this. Write an equation of the line passing through the point negative 6, 4, that is A, parallel to this line, and B, perpendicular to that same line. Well, if we want to write the equation of a line, we know we're going to use this point slope form. Remember, the point slope equation to build upon. All right, and if we want to write the slope of that line, and it's going to be parallel to this line, then we need to know the slope of this line. So let's see, let's find the slope of that line. That line has a slope that is given in the slope-intercept form of that equation. So let's write that equation in its slope-intercept form. So we would take the equation, and here it's already written. I'm solving for y, so I'll subtract 3x on both sides. And then I'll march through and divide by 4. Dividing here by 4, the 4's go out. Dividing here by 4, I have negative 3/4 x, and dividing here by 4, I get 7/4. And this really doesn't make any difference. I'm not interested in the y-intercept. I'm interested in the slope. So if this line has a slope of negative 3/4, then any line that's parallel with it will have a slope that is negative 3/4. Any line perpendicular to it will have a slope that is its negative reciprocal. That is, a perpendicular line, or a line perpendicular to that one, will have a slope that is positive 4/3, you see. All right, so that's the way we build upon the idea. Now, to do the A part, we set up our point slope form, or our point slope equation, and we plug in. The slope is negative 3/4 that we just calculated. And the point that we're talking about, we want that line to go through the point negative 6, 4. So x is replaced with negative 6 and y is replaced with 4. I should say x subscript 1 and y subscript 1 are replaced with negative 6 and 4. So negative 6 in place of x1, 4 replaces y sub 1, and it's a matter of manipulation from here. Minus negative 6 is plus 6. And remember, before we talked about here we have a jumping off place. We can expand and put this equation into general form, or we can put it into the slope-intercept form. Either one of those forms would probably be okay. I think in your textbook for problems like this, we're putting the problems into general form. And I mentioned that that form was ax plus by equals c earlier, but another form of that general form is ax plus by plus c equals 0. So either way, I think we can see the correlation between them. But at any rate, when we go through here and multiply by 4, 4 times y, 4y, 4 times 4, 16, and the 4's cancel here, leaving negative 3 times x plus 6, expanding over here, negative 3x minus 18, and then kicking all the terms to the left side. We'll add 3x and add 18 on both sides. I'm adding 3x and 18 here and here, and then collecting the constants, I find the equation to be 3x plus 4y plus 2 equals 0. And if we were working the B part, when we work the B part, and I'll just start it for you here. Excuse me, let me get an eraser. But if I'm starting the B part, and I'm not going to finish the whole thing, but we're going to use the negative reciprocal of that of the slope of that previous line, and that negative reciprocal is 4/3. And everything else stays the same in the problem. And we march down, and when the smoke clears on this one, we end up getting 4x minus 3y plus 36 equals 0, just to satisfy your curiosity.